Hello, my name is Omar. I'm one of your TAs for Digital Logic this semester, and this is Lab 5, You Aren't Cooked, a direct response to Lab 4, You're Cooked by Joseph Goodman, one of my fellow PIs. So, let's just start off with a review of Lab 4. So the first thing that we did is we started off with an ALU. You can see here, this would generate signals and then choose them with a multiplexer and then output the result. But we wanted to make it more powerful, so we added registers to expand it. So now, with Reg A and Reg B, we would be able to save the results of operations in the ALU, put new values in the registers from the input bus, make them hold their values. It was a pretty nice upgrade. So, where do we go from here? The obvious answer is to make something control the ALU for us. So, this is the motivation for Lab 5. If you remember when you were demoing your Lab 4 Part 2 or when you were doing the simulation, you were manually controlling every single part of the ALU. When you would have to manually select where the data from A would go, where the data from B would go, what operation the ALU was doing, the input bus. It was a lot of work. So we want to make that simpler. So what we do is that we add a controller to the ALU. What this will do is that it'll take in an instruction and then output the proper signals to the ALU to make it do the instruction. And you can see there's the controller. So a controller decodes an instruction into different signals for the ALU to use. You can say that a controller controls the ALU. You can do multiple ALU operations through a single instruction because the controller is a state machine. So you can do one ALU operation, move to the next state, and then do another one. So here's an example of the controller. So if you wanted to take the 2's complement of register A without the controller, just remember to take the 2's complement of a number, you negate it and then add 1. You would need a first output of signal to take the negation of register A, then put it in register A. Remember that 0, 1 will take the output from the ALU, which in this case 0, 0, 0 is negation. Cell B being equal to 1, 1 means that it'll hold the value. Then after that, we put 1 into the input bus, set select B to 0, 0, so it'll take the value from there. Then we add them with op-in equals 0, 1, 1. We use, for select A, it takes the output from the ALU, then we hold select B. So now we have the 2's negation of register A within register A. However, with the controller, it's a lot simpler. We pass in the instruction for 2's complement with A as des. In this case, the operation is 1, 0, 1, and the destination is 0, so the instruction is just going to be 1, 0, 1, 0. So we clock it once for the negation of A, we change the input bus to 0, 0, 1, clock again to put the value within B, we clock it once more, and then we're done. Rather than us controlling the ALU signals, the controller is doing it for us, and after every clock edge, it outputs the appropriate signal to perform the operations required. So here's another decoder example. The previous operation, 2's complement, is basically the most complicated one there is, and basically every single operation is simpler. For example, if you add 0, 1, 0, 0, the instruction is and the destination is A. You just said 0, you just said select A to take output from the ALU, select B holds its value, an operation in is 0, 0, 1 for and then you're done. So by using a controller rather than controlling the ALU manually, performing operations is now a lot easier. This, combined with other stuff, forms the basis of an assembly language, and this is how all CPUs at a fundamental level basically function. TLDR, a controller takes in instructions and outputs signals to the ALU. And now we're done. Or am I? Keep watching if you're curious how you would expand this lab theoretically in the future, but you're not going to be tested on anything past this, and this is more for personal knowledge. So I dubbed this Lab 5.1. This won't be extra credit or anything like that, but I thought it would be nice to describe a bit of extra stuff, how you would make a more complex CPU. So feel free to skip if you aren't interested in any of this nitty-gritty of the CPU stuff. The main part that adds CPU is memory. In this lab, you directly use the input bus for operations, but in real CPUs, they take values from memory. And when I say use the input bus for operations, I mean that you passed in the instruction to the controller manually. The decoder would control both the ALU control signals and the input bus. It does this by having a register called a program counter that increments after each operation is done. For an instruction like load, the value to be loaded into the memory or into the register would be located after the instruction, and this is called an immediate value. So for something like the 2's complement operation, we would have the 2's complement operation in memory, and then or the instruction for 2's complement within memory, and then after that, it would increment the program counter to move to the next instruction. For one where you have an argument, it would basically look at the instruction, see that it's a load, then it would move into a specific state, increment the program counter, then take that value and put it in a register. So rather than provide the decoder with the instruction manually, it would pull it from memory at the address specified by the program counter. Then after it's done, it increments it. There are special counter registers that have signals that allow you to increment them easily with the option to load a value in if needed. There's a lot more that can go into a CPU, like using external memory, cache, instructions with multiple arguments, branching, reset vectors, interrupts, etc. To learn more about that stuff, you can take computer organization, which is CDA 3101, which is required if you're in computer engineering or computer science, and microprocessor applications, EO 4744, required for CPE, and it's a tech elective for CS. And with that, that's about it. Have a good one.